Good morning. Myself, Guruswami K, Assistant Professor in Physics. Now I am going to deliver a fourth lecture on nanophysics. This topic belongs to Paper-6 of third BSc course, Kuompu University. Now I am going to cover the topics in this session are nanoelectronics, semiconductor structures like quantum wells, quantum wires, quantum dots. Recap of the previous session. The previous session we discussed about fullerenes, that is carbon-60 fullerene, their structure, properties and applications. And secondly, we are discussing the previous session, that is carbon nanotubes production, properties and their applications. Learning objectives of this session. After the completion of this session, students should be able to understand concept of nanoelectronics, semiconductor structures like quantum wells, quantum wires, quantum dots. Session outcomes. From this session, students will be able to know the basics of nanoelectronics, synthesis of nanoelectronic devices like quantum wells, quantum wires, quantum dots. Nanoelectronics. Now I am going to give a brief introduction connected with nanoelectronics. The most significant nanostructures required to design nanoelectronic devices are quantum wells, quantum wires, and quantum dots. They are the basic building blocks of nanoelectronic devices. In nanoelectronics also, we are going to control the transfer of electrons. But how to confine them, how to actuate them, how to fix the threshold level for conductance, all these questions will be answered when we understand the physics of these three quantum structures. As we know that in the bulk materials, where electrons are free to move in all the directions and no limitations or no confinement. In this case, electronic energy level bands will be crowded as well as will be almost continuous. Now we are going to discuss quantum well. What is quantum well? Where electrons are free to move only in two directions and confined to one direction. In this case, electronic energy level bands will not be crowded like bulk and with an increased gap between bands. The term well refers to a semiconductor region that is grown to possess a lower energy so that it acts as a trap of electrons and holes. They are referred to as quantum wells because these semiconductor regions are only a few atomic layers thick. In turn, this means that their properties are governed by quantum mechanics, allowing only specific energies and band gaps. Two dissimilar semiconductors with different band gaps can be joined to form a heterojunction. The discontinuity in either the conduction or the valence band can be used to form a potential well. That can be better illustrated with this diagram. This first energy diagram shows the energy gap and between the valence band and conduction band, and by using this, how we are going to construct this quantum well. Here, additional semiconductor layers can be included in the heterostructure. For example, a stepped or asymmetric quantum well can be formed by the inclusion of an alloy between materials A and B. Materials, this is energy gap, this is the material A and this is the material B. This is A and B. Okay, but there we are going to include or add some alloy between these two materials, then we are going to get a quantum well. Still more complex structures can be formed, such as symmetric or asymmetric double quantum well and multiple quantum wells or super lattices. Here the second diagram shows how we are going to design these quantum wells. Okay, these are the walls of this quantum well. This is look like a well structure, hence we call this as quantum well. Next, quantum wire. A standard quantum well layer can be patterned with photolithography or perhaps electron beam lithography and etched to leave a free standing strip of quantum well material called as quantum wire as shown in figure here. Okay, this is quantum well. Here we are going to etching or removing one of the walls of this quantum well structure, and the resulting one is what we call quantum wire. And here we found that the electron confinement can found in in two dimensions. The electron can move in only one dimension. Okay. Any charge carriers are still confined along the heterostructure growth z-axis as they were in the quantum well, but in addition, they are now confined along an additional direction, either x or y axis, depending on the lithography or etching. Next, quantum dot. Quantum dots can again be formed by further lithography and etching. That is, if a quantum well sample is etched to leave pillars rather than wires or wires, then a charge carrier can become confined in all three dimensions as shown in figure. Okay. These pillar-like structures can be leave in the case of quantum well design, then the resulting electronic device, nanoelectronic device is what we call quantum dot. Here this diagram shows the confinement of this charge carrier in all dimensions, that is x, y and z dimensions. Okay. In the case of quantum dot, electron confinement can found in all dimensions. In the case of quantum wire, electron confinement can be found in two dimensions. In case of quantum well, electron confinement can found in only one dimension. Like this, we are discussing the different electronic structures like quantum well, quantum dot and quantum wire. Thank you.